Okay, so here's another example. Determine the displacement at point C and the slope at support A of the beam. Okay, so we've got a simply supported beam in this case. We want to know the deflection at point C and the slope at point A. This is a little bit more obvious as a superposition problem. So we've got the point load and we've got the distributed load from A to C. All right, so let's work our way through this. So that's our combined loading, separated into two parts. So we have the part where we've just got the distributed load from A to C, and then the part where we have the concentrated load at the center. All right, so displacement at C and slope A. So if you look at our table, luckily enough we have a standard solution that we can get the slope and deflection directly from the table. Okay, so we can see that at end A we have this formulae, so indicating clockwise rotation. Okay, clockwise rotation here, and we also have the deflection at point C. So we need to make sure we get the right one here. So we don't want the maximum, because the maximum is not going to be at point C. Maximum is going to be somewhere else, right? And in fact it's given to you here, right? We want the deflection at x equals L over 2. Yep. So 5W L to the 3 on 768 EI. So put the numbers in and you get the deflection at point C. All right, so now let's look at the second loading. So simply supported, point load in the center. This one's a little bit easier. Okay, so the slope maximum, all we get is the maximum slope, so that's obviously going to be at the ends, and because the load's in the center it's symmetric, so both sides are the same. And the deflection will be maximum at the center under the load, so we can get those directly from these formulae. Alright, so now all we need to do is just add those up. Total displacement at C and the slope at A, we just add those together. Okay, so note here that we haven't used the signs. All we've done is used arrows to indicate the directions of the rotation and the directions of the displacements. Okay, all right, here's another example. In this case, we've got a beam sitting on two springs. The two springs are the same stiffness. So we're given the stiffness of the springs and we want to know the displacement at point C. Okay. So again, it's not superposition of loads this time, but a superposition of deflections. Okay. So we're going to have deflection of the two springs. So this beam will move as a rigid body, and then you'll also have the deflection of the beam itself. Okay, so you need to add all of those deflections together to get the total deflection. So before I show the next step, have a think about, if you've got the beam like this, what's going to happen? Which way is it going to rotate? Is it going to rotate this way as it moves down, or is it going to rotate this way as it moves down? Okay, so stop the video, get out your pen and paper and just draw what you think is going to happen. Okay, so one of the most important things in being able to do these problems is to be able to first visualize what the deformation and the displacement is going to be, especially when we come to doing the statically indeterminate problems. Okay, so how did you go with that? All right, so I've shown here that we're going to get a rotation that looks something like this. Now, why is that? If we do our equilibrium calculations, work out our reaction forces, right, because this force here is closer to the end A. So do sum of the moments equals 0 for equilibrium. We should see that this force here is greater than the force over here. So from F equals Kx, the spring equation. So if we've got twice the force on the left here as we have on the right, then this is going to deflect twice as much as we have on the right. Okay, so from F equals Kx we can get those deflections, and once we have those we can determine this deflection here. Okay, because this is a straight line, we can just simply, for now, we can simply use the ratio of these lengths here to get the deflection at point C. Right, so if we do that, this is what we get. Okay, so the deflection at point C here will be the deflection at point B plus this deflection here, which is just 2 over 3 times this deflection at the end. Okay, so get my stick again. So if I rotate like this deflection here, right, so if it was halfway along, right, it's pretty obvious that the deflection here will be half what it is at the end. Yep. So if it's 2/3 of the way along, then the deflection here will be 2/3 of what it is at the end. Yep. Okay. And then after this, we consider the fact that this beam is not rigid, right? It itself can deflect, so this deformation here will be superimposed on this rigid body motion. Okay, so let's work out what that deflection will be. So now we need to look at the table, and I'm not sure if yes, I did put it in for you. So here, look at our standard formulae for our cases. So we have a case that looks like this. So we can just put in our values, so A and B for where the load is, and we can calculate the deflection. All right, so that's all pretty straightforward. And then once we have that, we can combine that together. So we have our rigid body deflection of the beam because of the compression of the springs, and then we have this deflection here, so we add this to what we had up here, so we get a total deflection of 38.4 millimeters. Okay, one more example, I think. So this one we have something a little bit different. So it doesn't look like your standard beam cases that we've been looking at so far, but we can still make use of those standard case formulae. Okay, so here we have an elbow, a rod bent into this elbow shape, a load here, and we need to work out the deflection at point C. Okay, so it's not really superposition as such because we're not dividing the loading, but what we're doing is adding the various deflections like we did with that beam problem sitting on the springs. We're just adding the deflection and rotation to get the total displacement. Okay, so deflection at C consists of 3 parts. So we have torsion of AB. Okay, so if this is our beam, right, if we rotate, okay, so my shoulder here is point A, my elbow is point B. So if we simply rotate, then we get a deflection here. Okay, so torsion of AB gives us that. Okay, so in the same way we did previously, where we calculated the angle here, if we know this length, this displacement is just angle times the length. Yep. Then we have the bending of AB. So this force out here is going to cause this to bend down, and then BC here is also going to bend from B to C. Okay, so 3 components of the deflection. Alright, so in this video we've got pretty much the solutions come up, but I've done a very similar problem to this a few years ago, and you can click on this link from inside the PDF or from down below in the comments on YouTube. Okay, so determine the deflection at C due to deformation of AB first. So firstly we have torsion of the rod AB, so you just need to look up the angle of twist formula, and then so the angle of twist for AB, and then multiply by this length here to get that displacement due to the torsion. Okay, note that this equation here, PL squared upon GJ, is not a general formula, right? It just works out like this in this problem because this length here is the same as this length here. Yep. Okay, so then we have the bending of AB. Right, so this will bend down here, so all of this will move down with it. Okay, so this is just a cantilever beam case that we saw previously in previous examples. So that would just be PL cubed upon 3EI. And then the third part will be the bending of BC. Okay, so again, what we're doing here is considering that from my shoulder to my elbow is rigid, and then this will bend down due to the force that's applied on here. Right, so if I force here, that's going to bend down like this. Yep. Okay, so once we have all of those, we just add them all up and we can calculate that total downwards deflection. Okay, so as I said, if you want to see a fully worked solution, step by step of this, go to that that video I showed you, and the link will be down below. Okay, so I'm going to stop here and then do the next video on statically indeterminate beams and shafts and show you how we use the deflection and, sorry, look at the camera, show you how we look at deflection in order to solve for statically indeterminate problems. All right, catch you in the next video. Bye for now.